Hello, I'm very happy to share with you today. My presentation is Ancient and New Tunings, Creating New Paradigms in Music, a presentation with musical excerpts. My name is Michael Harrison. I'm a composer and pianist living in New York City. I'm one of a few musicians with equal training in both Western and Indian classical music. My father, David Harrison, was a mathematician specializing in abstract algebra. My paternal grandfather, George Russell Harrison, was a physicist specializing in spectroscopy and the Dean of Science at MIT. I have over 40 years exploring the sonic dimensionality and potential of just intonation. Tuning systems have gradually changed and evolved over the centuries. These shifts have often opened the possibilities for new paradigms in music. For the past 2 centuries, Western music has been dominated by equal temperament. With new interest in just intonation and microtonality, we may be at the beginning of a new paradigm shift in music. I'll tell you a little bit about my story. I grew up playing the piano from an early age, and when I was around 20 years old, I started singing every day North Indian classical music, and I was studying with Pandit Pranath, who's a master Indian vocalist, and his senior disciples, the composers Terry Riley and Lamont Young. After about a year of singing ragas every day, accompanying myself with the tambura, which are these Indian lute instruments you can see in the background, which create deep and beautifully rich drones, my main instrument, the piano, started to sound out of tune. So I called the piano tuner and had him tune it, and it still sounded out of tune. So I was very curious what was going on, and I started studying the physics of sound and acoustics. And what I realized is that the way the piano and Western instruments are tuned today is a compromised system that in order to have all of the notes equally spaced, the actual purity of the resonance of each note has to be a little bit out of tune, in some cases even more than a little bit out of tune. And by learning to sing in what we call just intonation, which is true tuning, with the Indian ragas, it had changed my whole way of hearing. And this was the beginning of a lifelong journey for me, exploring different tuning systems and specializing in just intonation. Now let's begin with the harmonic series, which is the most fundamental principle in the physics of sound. Musical instruments make the air vibrate, creating sound waves which travel to our ears. Even when only one note is played, there are many frequencies produced at the same time. The primary note is called the fundamental, but along with this there are many other notes which are called harmonics. Harmonics vibrate at integer multiples of the fundamental. At the fundamental pitch, 2 times the fundamental frequency, 3 times, 4 times, 5 times, etc. Harmonics create an infinite variety of tone colors that let us know whether we're listening to a violin, clarinet, or piano. The higher the notes, the faster the string, column of air, or membrane vibrates. For example, an A above middle C vibrates at 440 Hertz. That's 440 times per second, producing the fundamental or first harmonic. The second harmonic vibrates twice as fast at 880 Hertz, creating a ratio of 2 to 1, which produces an A an octave higher. So anytime you have a ratio of 2 to 1, it creates a musical octave in which the upper note is vibrating exactly twice as fast as the lower note. The third harmonic vibrates 3 times as fast, creating a ratio of 3 to 1, producing an E, an octave and a fifth above the fundamental. Generally, the higher the harmonic, the quieter it is. And the ratio is always a whole number proportion, and not a fraction or irrational number. Now here's a diagram showing what the periods of pure tone harmonics would look like. So this is as if you have a string vibrating at the fundamental, which is 1, then at the second harmonic, which will create a node in the middle and vibrating on either side, and this creates the note an octave higher. Then with two nodes at 1/3 and 2/3 the distance of the string, it creates the note an octave and a fifth higher. And this continues. Now, if we were in real life, I would have a large rope on the stage, and I would demonstrate these modes of vibration with the rope simply by making my hand move faster and faster to get the higher modes of vibration. This next diagram shows you what a string actually would look like when it's vibrating if you could see all the levels of vibration. You can see the octave, which is the large arc on the outside, and how the different harmonics get smaller and smaller as they get quieter and quieter and higher in pitch. Now here is the harmonic series with musical notation. So you see, let me go back up, and now I have the pointer. So the lowest note on the left is a low C, and that's our fundamental frequency. The fundamental frequency can be any note, but once you establish the note, then on a musical instrument, it will create the same harmonic series. The second harmonic is the note C again, an octave higher. The third harmonic is the note G, an octave and a fifth higher. The fourth harmonic is the note C again, higher still. The fifth harmonic gives you the note E, and the sixth harmonic gives you the note G. The seventh harmonic is a very low B flat. The eighth harmonic is the note C again. So let's take a look at a few things here. First of all, anytime the harmonic is doubled, for example, 2 to 4 to 8 to 16, it'll just give you another octave higher. So those notes are all the note C. Or if we take the third harmonic G and we double it, we'll get 6, and we'll get G again, double it, and you'll get the 12th harmonic, which is G again. Also, notice that between the 4th, 5th, and 6th harmonics, you have the notes C, E, and G. That's the so-called major triad, or chord of nature, the most important chord or harmony in Western music. Now, one of the things that I want to stress is the most important thing about this harmonic series and how it relates to new paradigms in music is the prime numbers. So the prime numbers, I have them written out here, are 2, 3, 5, 7, 11, 13, 17, and 19. And of course, this goes on theoretically to infinity. Each prime number introduces a whole new dimension in tuning or in sound or harmony. So when we get to the third harmonic, we get the interval of a perfect fifth. The relationship of 3 to 2, where one note is vibrating 3 times for every 2 vibrations of the lower note, is the most stable interval in music. And from that one interval alone, we derive one of the most important tunings, the Pythagorean tuning. That's all you need, is that one interval, and to stack it in various combinations. The next harmonic, 4, is not a prime number, and it doesn't give us anything new. It only gives us the note an octave above the second harmonic. But the fifth harmonic is a prime number, and this note E, cannot be generated from any of the previous notes. So it requires this harmonic to create a whole new harmonic language. And this is the language that Western music is based on, up to the prime number 5. Combinations of the perfect fifth, which is the 3 to 2 relationship, and combinations of the major third, which is the 5 to 4 relationship. When you stack those two intervals together in many different combinations, you get all the complex harmonies of Western music from Bach through Debussy. Now, what I'm proposing is that when we get up to the seventh harmonic, which is the next prime number, we get an interval that is not included on the piano. If you look above the note, it says -31. That means that this note is 31% of a half step, that's the smallest note on a piano, lower than how it would be tuned on a piano. So the normal B flat on the piano would be 31% higher than this natural harmonic. That means that this note really doesn't exist on the piano and most Western instruments. However, when you tune it on the piano, or use it with voices, for example, you introduce a new harmonic language, which has, I believe, tremendous potential for the future of music, as does the higher primes 11, 13, and on. Now, the simplest whole number proportions give us the most consonant musical intervals. And this would have been one of the first things that you would have learned if you were studying music theory or learning to tune your instrument in the Renaissance. So the sequential consonances in the harmonic series, in this case in the key of C, would be a one-to-one relationship. For example, a piano and violin are playing the same note C, so we call that a perfect unison. 2-to-1 relationship, we already found, is a perfect octave. 3-to-2 relationship is a pure perfect fifth. That would be for the notes C to G, for example. 4-to-3 would give us a pure perfect fourth from the notes G up to the C above. 5-to-4 gives us our just or pure major third from C to E. And 6-to-5 gives us our just minor third from E to G. So these are the most consonant intervals that exist in music, and you can see they're also the simplest whole number proportions. We also get a few consonances that occur in non-sequential tones from the harmonic series. For example, 5-to-3, which gives us the just major sixth from G up to E, and 8-to-5, which gives us the just minor sixth from E to C. Now, if we go to the next slide, we see that more complex whole number proportions give us more dissonant musical intervals. So the so-called whole step can be either a 9-to-8 relationship, which gives us what we call the greater tone from C to D, or it can be the 10-to-9 relationship, which we call the lesser tone from D to E. Now, in just intonation, these two different whole steps are different musical intervals. However, the way they're tuned on the piano, they're identical. And we'll get more into that later. 16-to-15 gives us our minor second or semitone. 15-to-8 gives us our just major seventh, and etc. You can see they get more complex. I'll say a little bit about the last two on this list. 45-to-32, the augmented fourth or tritone, is a very famous interval in music. In the Renaissance, it was considered so dissonant, it was called the Diabolus in Musica, the devil in music. And it always had to be used in a certain way and resolve. The very fine interval of 81-to-80 is the syntonic comma. And we'll talk a little bit more about these commas later, but commas are when you have two slightly different versions of the same note achieved through a different harmonic pathway. And this is where you get interesting microtonal relationships. It's because of these commas that tempered tunings, the tunings that we use in Western music today, were created, because these commas were considered so dissonant they had to be avoided. Now, the Pythagorean tuning is perhaps the oldest and simplest complete form of tuning in the world. It's completely based on the ratio 3-to-2, or the perfect fifth. 3-to-2 produces the most consonant and stable musical interval and the easiest to tune by ear. This system has mainly been attributed to Pythagoras from the 6th century BC and was used by musicians extensively up to the beginning of the 16th century. The Pythagorean system would appear to be ideal because of the purity of the fifths. But some consider other intervals, particularly the major third, to be so out of tune that major triads actually create a dissonance. Now, here's a diagram showing a little bit about how the Pythagorean tuning works. So if we start on the note C, for example, and we go around a series of perfect fifths up to G, D, A, E, B, F sharp, C sharp, G sharp, D sharp, A sharp, F, and then we'll come back to C again. Now the way the piano is tuned today, those two Cs are the same note. But if you do this in Pythagorean tuning, the C that you'll end up with after going around a series of 12 fifths will be slightly a higher pitch than the C that you started with. In fact, it's almost 1/4 of a semitone. So what this means is then rather than creating a circle of fifths, it creates an infinite spiral which spirals on into infinity. The mathematical explanation of this is each fifth is a multiple of 3 because the fifth comes from the third harmonic. So multiples of 3 are never divisible by 2. 2 is the second harmonic, which gives us the octave. So this means as long as you tune by a series of fifths, you will never get octaves. Here's a diagram of how the Pythagorean tuning works, the mathematics of it. So for example, if we start with the note C, we would go up a series of fifths, G, D, A, E, B, F sharp. Then usually we also go down a series of fifths, down to F, B flat, E flat, A flat, G flat, D flat, and G flat. So if you go to the right, you get the natural and sharp notes, and if you go to the left, you get primarily the flat notes. And the mathematics of this is that you just take 3 to 2 and multiply it by itself, and then either multiply it or divide it by 2 to bring it into the correct octave. If you're going down the fifths, then you invert 3 to 2, which gives you 2 over 3. Then you multiply it by 2 to bring up an octave, you get 4 to 3. 4 to 3 times itself, a perfect fourth of a perfect fourth would give us 16 to 9. And down below are the cents that show you how this relates to the tuning of the way the piano is tuned today, which is called equal temperament. In equal temperament, for example, this note here would be 700 rather than 702. This would be 200 instead of 204. So as the notes get further away from your root note, C in this case, they start getting more and more out of tune with the equal tempered scale. Now I'd like to play you a musical excerpt. So organum is a plain chant melody with at least one voice added to create harmony. And these simple harmonies that were originally improvised, at least in Western music, were the beginning of harmony and polyphony, which are two of the most important developments in Western music. Usually a Gregorian chant melody and the same melody is transposed by a perfect fifth or fourth occurring at the same time, creating the harmony. This type of music was developed in the Middle Ages. Gradually, composers began writing more independent parts, thus creating true polyphony. True polyphony is where each voice has a more independent part than you'll find that if it's just in parallel fourths or fifths. This type of music was mostly in the Pythagorean tuning. That means that the highest prime number from the harmonic series was the prime 3. And as you see, as we evolve up the prime numbers, the music, each time a new prime number is introduced, gives us a new kind of dimension in sound. So let's take a listen to the first few minutes of this. So that gives you the sound of perfect fourths and fifths in harmony. All right, now we come to just intonation. Just intonation is any musical tuning in which the frequencies of notes are related by ratios of whole numbers. The two notes in any just interval are members of the same harmonic series and are called just or pure. Historic just intonation uses only notes derived from multiples of the prime numbers 2, 3, and 5. But now, with some pioneering composers, we have what we call extended just intonation, which includes higher primes, such as 7, 11, and 13. Just intonation survives today mainly with a cappella vocal music and in Indian ragas. And here's a nice definition for just intonation by Bob Gilmore. Just intonation is the tuning system of the latter ancient Greek modes as codified by Ptolemy. It was the aesthetic ideal of the Renaissance theorists and is the tuning practice of a great many musical cultures worldwide, both ancient and modern. Now I'll play you an extremely early example of just intonation, which is a technique called Jamel, which is harmonizing chants with thirds and sixths. This occurred in medieval and early Renaissance English polyphonic music. The earliest examples date from 1430. The thirds that you'll hear in this are tuned in just intonation, and they're based on the fifth harmonic as the highest prime from the harmonic series. You'll hear that the sonic texture and sensuality of these harmonies is of a completely different dimension than the organum that we just played a moment ago.
C'est-à-dire comme mélodie de base, la chanson du chansonnier de Bayeux, puisque Robin j'ai un nom. Lise et Marie chanteront le début de cette mélodie à l'unisson, puis Marie continuera le cantus firmus, tandis que Lise improvisera le gimel.
So the harmonies created by those thirds are what gave rise to the entire musical language that has been used ever since the Renaissance, all the way from Palestrina up to Debussy. And so it's very important to remember that this language was introduced when the fifth harmonic from the harmonic series started to become a common part of the musical vocabulary. Now, I'd like to introduce you to an excellent book, because now we're going to speak for a minute about temperament. This is by Stuart Isikoff, How Music Became a Battleground for the Great Minds of Western Civilization. So temperament tells the story, beginning with Pythagoras, through just intonation, how temperaments were invented, and all the great thinkers of the Renaissance, from Newton, Galileo, Descartes, even the artist Leonardo da Vinci, and various popes and heads of state got involved in this. It was like a major artistic, cultural, and political battle that went on for hundreds of years, because the pure intervals of just intonation were considered to be sacred. And so to temper them or change them to have them fit equally on a keyboard was considered to be playing with the rules of, or playing with the rules of God or of nature. So I'll read you just a short excerpt from Stuart Isikoff's book. Harpsichords and organs, precursors of the piano thus tuned, were capable of producing harmonies of magical, uncorrupted sweetness in one moment, and as musicians attempted to duplicate them while navigating the spans of the keyboards, of ear-splitting clashes the next. These are the commas or wolf tones that result from just intonation on a keyboard. Composers were prisoners of these torturous practicalities, as were vocalists and instrumentalists who tried to join in. Yet the resistance to a remedy that we find perfectly acceptable today, the tuning of equal temperament, was so powerful, the idea was for generations almost unspeakable. The crux of the problem can be traced to the ancient Greeks, who defined music's most beautiful sounds as arising from inviolable mathematical relationships, the fingerprints of the gods. These were the proportions through which two separate tones could entwine to form a delightful union. Centuries after Pythagoras conceived of the notion, the great astronomer and musical theorist Johannes Kepler restated the idea eloquently. Geometry existed before the creation, is co-eternal with the mind of God, is God himself. Musical harmony was that geometry made sensual and was not to be toyed with. And yet, as the art of music evolved, a startling paradox arose that threatened to undermine the entire arrangement. When harpsichords or organs were tuned so that they could consistently produce sounds corresponding to one of the venerable formulas, which are the ratios that we've been discussing, they were rendered incapable of playing the others. No instrument with fixed, unbending pitches such as the piano can accommodate them all. Thus, certain combinations of tones that should have sounded sweet and placid could, on an early keyboard instrument, become sour and ragged. In search of a solution, musicians began to temper or alter their instrument's tuning away from the ancient ideals. The final solution, today's equal temperament, abandoned most of the revered musical proportions altogether. This book begins with Pythagoras and ends with a description of a concert of my work, Revelation, which Stuart Isikoff attended. And we'll play some excerpts from Revelation at the end of my presentation. So equal temperament, which is the most common tuning for Western music over the last few hundred years, approximates just intervals by dividing an octave into 12 equal steps. Equal temperament has been the most common tuning since the 18th and 19th centuries. It eliminates the discordant clashes. However, it severely compromises pure intonation, harmonic resonance, sonic beauty, clarity, and diversity in intervallic relationships. Unlike just intonation, which creates periodic waveforms, equal temperament creates non-periodic waveforms, meaning the waveform actually never repeats itself. And then here's the math at the bottom of how equal temperament is created. So equal temperament, which is hailed as the ultimate tuning and has created so much great music over the last few hundred years, is really only one solution, and it is not a perfect solution by any regards, because what happens as a result, the only interval that is still in tune with these perfect harmonic proportions is the octave, 2 to 1. Everything else is out of tune with the natural resonances of sound. The reason it works so well is that the perfect fifths are only 2% of a half step flat in equal temperament, but the thirds are 14% of a half step sharp, and the harmonic sevenths are 31% of a half step sharp. So my proposal is that by exploring various tuning systems, we can introduce a much greater diversity in the world of music. Now, if you remember the Pythagorean infinite spiral of fifths in equal temperament, those fifths are all shaved down a little bit, so instead of becoming a spiral, when we go around the circle, starting at C to G to D, we'll eventually come back to the same note that we started with. And this obliterates that Pythagorean comma, which is the small gap from one version of a note to the next note. Now I'll do a quick review of tuning systems. So we already discussed the Pythagorean tuning, the ancient tuning based on the series of 3 to 2 ratios of perfect fifths. Just intonation, the theoretical ideal of the Renaissance, based on a series of 3 to 2 and 5 to 4 ratios, perfect fifths and pure thirds. Then for a few hundred years, there were many historical temperaments. These are mostly from the Baroque era. Mean tone tuning favors pure thirds, but at the expense of the pure fifths. And well temperament is most likely one of the tunings that Bach used for his well-tempered clavier. There's a common misnomer that because Bach composed music in all 24 keys, 12 major keys and 12 minor keys, that it must have been equal temperament. But in fact, it's an earlier form of temperament where notes are tempered in a way but not equally, so that you can still play in every key, but each key will have a different sound, unlike today, where each key basically plays the same interval just at a higher or lower pitch. Equal temperament is the current Western standard with 12 equal divisions of the octave. Now in modern times, and also in various forms of non-Western music, microtonality is explored. This uses notes in between the 12 notes on the piano. Extended just intonation is a form of just intonation that includes higher primes, such as 7, 11, and 13. Quarter tones gives you, instead of 12 equal divisions of the octave, 24 equal divisions of the octave. So it's like equal temperament, but twice as many notes. And you can also divide the octave into other equal divisions. For example, 13 divisions to the octave, 17 divisions of the octave, or even 72 divisions of the octave. There are various systems that composers are working with today. I'd like to introduce you a little more now to the prime number 7 from the harmonic series and how it creates a new musical language, which I explore in much of my music. So these are some of the intervals that occur that did not occur in the earlier forms of just intonation and which do not occur in any way on the piano. 7 to 4 is the most common. That's the pure harmonic seventh, the distance between the 7th and 4th harmonic of the harmonic series. And then at the bottom of this list is another comma, we call the septimal comma because it's derived from the prime number 7, which gives you two slightly different versions of the same note, a 64 and 63 harmonic apart. The pioneering composers working with extended just intonation are Harry Partch, who passed away in 1974. He was an American composer, music theorist, and creator of musical instruments. He created his own 43-tone scale in just intonation, and he was one of the first composers in the West to work systematically with microtonal scales. Then my teacher, Lamont Young, born in 1935, recognized as one of the first American minimalist composers and a central figure in the post-war avant-garde. He is best known for his exploration of sustained tones and for his 6.5-hour work for piano in just intonation called the Well-Tuned Piano. Now, I'd like to play you the first movement of my work called Just Constellations, because we've listened to two vocal pieces, the first one using primes from the harmonic series up to 3, the second one using primes in the harmonic series up to 5, and this one now uses primes up to the number 7. And the whole harmonic language of this piece is based on these new harmonies that result from using a higher prime in the harmonic series. This piece was recorded by the vocal group Roomful of Teeth in the tank, which is a 65-foot tall ancient water tank on the western slope of Colorado with extraordinary acoustics. I'm going to go ahead and take the time to play you the entire first movement, which is 8 minutes long, because I want you to hear how the architecture unfolds, starting very softly and very simply, and then building over time in a large arc. If you have quality headphones, now's the time to use them. So you can see or hear that by introducing just intonation and the seventh partial or the seventh harmonic from the harmonic series, you get a natural harmonic language which has really not been a part of our Western music culture, or most world music cultures for that matter. So by extending just intonation tuning into the higher harmonics, we open up a new dimension in sound. And of course, different types of tunings can be used for different types of music. For example, if you put a piano in this reverberant space the tank played, it might sound somewhat discordant because the incredible acoustics would amplify the compromises in the tuning. Whereas any type of music with sustained tones and long notes like in the piece you just heard, just intonation is ideal because the tuning will be perfectly in tune and the resonance will build and amplify on itself. So I'd like to finish my presentation today talking a little bit about my work Revelation and the tuning, and then I'll play you a few excerpts from it. So this is a work that is 90 minutes in totality. It is a fully scored work. I've performed it many times in various parts of the world. The tuning system is my own invention. It's based solely on the intervals 3-2 or perfect fifths and 7-4 or the pure harmonic sevenths, like you just heard in the Just Constellations vocal excerpt. It uses extended just intonation with seventh as the highest prime number from the harmonic series. The tuning itself is color-coded between the black and white keys, making it extremely intuitive to play. And there are 3 adjacent pairs of septimal commas. This is one of these small microtonal intervals. These are tuned to the adjacent notes F and F sharp, G and G sharp, and C and C sharp. And when you play these notes, they shimmer and they pulsate, creating their own rhythms. So the way the tuning works is the white keys are simply tuned in Pythagorean tuning, starting on the note F, a series of fifths, F, C, G, D, A, E, and B. And the black keys are also tuned in a series of Pythagorean fifths, starting on E flat to B flat, to F sharp, to C sharp, and G sharp. What gets interesting is the relationship between the black to white keys is all based on this pure harmonic seventh, 7-4. So the note E flat is the seventh harmonic above the note F. The note B flat is the seventh harmonic above C. The note F sharp is the seventh harmonic above G, etc. So you get these very interesting shimmering relationships when you combine the black and the white keys. And the last thing I'll talk about is the emancipation of the comma. The dissonant sound of commas was avoided throughout the entire history of music. Avoiding the sound of the comma was in fact the reason temperament was created in the first place. So in the Renaissance, the commas were considered so dissonant they were called wolf tones because they reminded people of the howling of wolves, and they were definitely avoided in all of the music. And then temperament itself, like equal temperament, takes the Pythagorean comma and divides it into 12 equal pieces so that you don't really hear it anymore, except that there's a subtle compromise to each of the fifths as they're no longer pure. These commas create pulsating and shimmering sounds with their own acoustical beats. And here are some of the 3 main commas: the Pythagorean comma, which we talked about, the syntonic comma, and the septimal comma, which is the one that is used extensively in my work Revelation. All right, here is the opening section of Revelation, along with the score, which you can follow along. And even if you don't read music, you can follow along because in the whole first section, I put in numbers above each note the harmonic that it is. And I'll follow along with you. Sorry, I thought I had that loaded up. Here we go. So to some of you, that might have sounded out of tune because we're so used to the piano being tuned in equal temperament that when you hear it in this tuning, it can sound quite different than what we're used to. In fact, it always sounds quite different than what we're used to. But the more you listen to it, the more natural it sounds. So I'll close my presentation by playing a 15-minute excerpt from my last concert of Revelation, which was in Rome right before the COVID breakout. And this is highlights, video highlights from that performance. This section will begin with Tone Cloud 2, which is about 1/3 of the way into the piece. And at this point, you're hearing many of these commas sounding simultaneously, creating the kind of pulsating rhythms that I was talking about. Thank you so much for joining my presentation today. It was a great honor to be able to present my work for the Sciences Meets Arts Conference. Thank you.